Hello students, welcome back. Students, in previous lecture we discussed Raoult's law in case of liquid-liquid solution. So students, based on the topic that is Raoult's law, now we will discuss some numerical problems. So I have two different questions. Now students, the first question is the molar ratio of volatile components A and B in a liquid-liquid solution is 4:1. What is the vapor pressure of this solution if vapor pressure of A and B in pure states are 100 millimeters and 200 millimeters of mercury respectively? So students, in this question we have to find out the vapor pressure of the solution. Now, so what is the vapor pressure of the solution? Now, the molar composition is given and the vapor pressure of the liquid components A and B in pure states are given. So students, we need to find out pressure P over the solution, which will be the partial pressure A और B का sum होगा. Now, according to Raoult's law, this will be what? P naught A x A, and this will be P naught B x B. These x A and x B are the mole fractions. Now, students, P naught A, that means the vapor pressure of A in pure state is 100 millimeters into mole fraction of A plus P naught B is 200 into mole fraction of B. Now students, mole fraction of A and B कितना होगा? Now students, number of moles A के 4 है, B के 1 है. So mole fraction of A will be number of moles of A, that is 4, divided by total moles. So it is 4 upon 5. So this is 4 up by 5 plus 200. So this will be now mole fraction of B is 1 upon 5. So this is 1 by 5. So students, the total pressure of the solution therefore will be, see students, this is 5 into, sorry, so this is 20 into 4, 80, plus we have 40. So students, the vapor pressure of solution is 120 millimeters of mercury. So this is how we find vapor pressure of solution using Raoult's law. Now students, we have another question. The vapor pressure of pure liquids A and B are 450 and 750 millimeters mercury respectively. So in pure states, the vapor pressures of the components are given at 350 Kelvin. Find out the composition of the liquid mixture. That means we need to find out now how many moles of A and B, or what is the mole fraction of A and B in the solution. And the vapor pressure of the solution is 600 millimeters mercury. And also find the composition of the vapor phase. So students, first we'll find out the composition in the solution phase using Raoult's law, which is P is equal to P naught A x A plus P naught B x B. Now students, see, the total pressure is given, it is 600 millimeters. Pure A का है 450 and mole fraction of A is x A. We have second component whose vapor pressure in pure state is what, 750, and xp can be written as 1 minus xa. We can relate total pressure to any of the components. So here I am relating it to one of the components. Now students, from this we'll calculate, see, 600, this is 450 xa plus 750 minus 750 xa. So students, from this we find out 750 minus 450 XA is equal to what? 750 minus 600. So from this we can find out mole fraction. 750 में से 600 less कर दिया, so this is 150 divided by 750 minus 450. So 750 minus 450, we have what? 300. So students, solving this, we get mole fraction of one of the component. So it is say 5 3s are 15, 3 by 6. So students, it is 1 by 2 actually. So 0.5. So we have mole fraction of one of the component 0.5. So therefore, what will be the mole fraction of second component? It will be 1 minus 0.5. So students, it is 0.5. So we have mole fractions of A and B in the solution as 0.5 each. Now students, we have the second part. Find out the composition of the vapor phase. Now we need to calculate the composition in vapor phase. तो vapor phase में composition कितना होगा? So students, in vapor phase composition is determined from Dalton's law, and we know that in vapor phase mole fraction से उसको मैं YA से लिखता हूँ. In vapor phase we write YA. It will be partial pressure of A upon total pressure, and partial pressure of A is what? P naught A into XA divided by total pressure. Now students, will determine these. Now A naught ka, it is given 450. Mole fraction in the solution we have determined 0.5, that is half, divided by total pressure. Now students, total pressure would be 450 into 0.5 plus what? It will be, the other component is 750 into 0.5. So students, from this we determine mole fraction of A. So 450 ka half would be 225. So this is 225 plus 750 ka half, this will be 325. Half of, so this will be 325. Now students, this will be half of this, we'll divide 2 3 is 6, 375. This will be 225. Now students, this is 225 divided by, so 375 plus 225, this is 10, we have 10, 5, 6. So students, we will solve this now to find mole fraction of A. इसको further divide कर लेते हैं. So 5 4s are 20, then we have 5 5s are, and then 5 1s are 5. So this is 1 20. Now this is further 5 9s are 45. This is 5 2s are 10. Then we have this. So this is 9 upon 24, which can be written as 3 upon 8. Or solving this, we get 0.8 3s are 24. We'll have 6 0. So this is 0.37. So now students, the mole fraction in vapor phase is 0.37. ये तो एक component का है. So students, similarly, what will be the mole fraction of other component? It will be 1 minus YA, that is 1 minus 0.37. So 1 में से 0.37 less कर दो, it will be 0.63. So students, this is how we find mole fraction in vapor phase. Now in vapor phase we use Dalton's law, but for Dalton's law also here we need Raoult's law. So this is how the mole fraction in vapor phase and solution phase are determined. Now students, we will move on to the next topic, which is vapor pressure of solid in liquid solutions. In this case, that is solid in liquid solution, our solid is actually non-volatile, solute. So we are considering solid to be a solute, and kaisa? It is non-volatile, which means it does not form vapors. Means इसका vapor phase में कोई contribution नहीं होगा, so that means total pressure में भी इसका कोई contribution नहीं होगा. And students, liquid will act as solvent, and we are assuming it to be volatile solvent. So that means vapor phase में जो भी vapors होंगे वो इसी liquid solvent की वजह से होंगे, and let this liquid solvent be A and solute be B. So students, एक बात मैं clear कर दूं, that suppose if this is a closed vessel and this is the volatile liquid A, students, at any given temperature in pure state we have only molecules of A which are forming vapors, and at some stage there exists an equilibrium between the molecules in vapor phase and those in liquid solution. So this is, say, equilibrium, and the pressure exerted by these vapors on the surface of liquid, we call it vapor pressure of pure solvent, so we are denoting it by P naught A. So this is the vapor pressure exerted by these vapors in pure state. Now students, when we add a non-volatile solid to this solvent, what happens, students? Now we will have some molecules of B also in the solution, but they will be present not in the bulk, but they will be at the surface also. So यहाँ पर भी कुछ जगह अब कौन लेगा? We will have some molecules of what? B. अब लेकिन B तो volatile है नहीं, so B vapors तो नहीं बनाएगा, but students, इससे surface area जो liquid का था, liquid that means pure component का, वो कम हो जाएगा, and now we will have less vapors in the vapor phase, and therefore students, अब जो इस solution का vapor pressure आएगा P आएगा, और वो P इस P naught से कम होगा. So that means एक बात तो बिल्कुल clear है, that when we add a non-volatile solid solute to a volatile liquid solvent, the vapor pressure of resulting solution what will be less than that of pure solvent. Now students, आपने एक बात तो देख लिया कि अब जो वेपर प्रेशर है वो है तो A की वजह से, लेकिन B के होने से वो वेपर प्रेशर ओरिजिनल वोलेटाइल लिक्विड यानी प्योर लिक्विड से कम आएगा. अब वो कितना होगा, that we'll understand. So students, we are assuming liquid to be volatile. So according to Raoult's law, at a given temperature, the partial pressure of A means A कितना contribute करेगा? We know it is what? Equal to P naught A into mole fraction of A in the solution. So we are assuming we have XA moles, mole fraction in the solution. So this is our first case. But students, solid is non-volatile. So being non-volatile, it will not form vapors. So its contribution to the vapor pressure is 0. And therefore the total vapor pressure P in this case will be equal to the partial pressure of A only, because B का contribution 0 है. So it is A. So or we write it as PA according to Raoult's law is what? It is P naught A XA. So students, finally we have that vapor pressure over the solution is P naught A into XA, or we say P is directly proportional to XA. So students, in this case, Raoult's law states that at any given temperature, the vapor pressure of a solution containing a non-volatile solid in a liquid solvent is directly proportional to mole fraction of the solvent. So this is very, very important. So listen carefully. The vapor pressure of solution is directly proportional to mole fraction of the solvent only. Kab, students? When we have a non-volatile solid solute. So when we plot this graphically, students, see this. So we are plotting mole fraction against, say, the vapor pressure P. Now students, see, at this point we have X A, say, 0 and XB what? 1. But B is non-volatile. So students, non-volatile है तो vapor pressure B की वजह से तो होगा ही नहीं, क्योंकि वो तो non-volatile है. So A की वजह से भी नहीं होगा, क्योंकि उसके तो कोई भी moles solution में है ही नहीं अभी. So at this stage we say अभी जो vapor pressure है वो 0 है. But students, धीरे धीरे अब mole fraction of A बढ़ता जाएगा और यहां पर आके mole fraction of A becomes maximum, that is 1, and B becomes 0. But students, X का mole fraction बढ़ता जाएगा तो vapor pressure भी तो बढ़ता जाएगा अब solution का, और ये suppose इतना हो गया. And at this point the vapor pressure जो भी होगा, now this is of pure A, B तो है ही नहीं, and this is called P naught A. So this graph will give the vapor pressure of solution as a function of mole fraction of solvent. So students, this was very, very important case. Now students, the next topic we have is Raoult's law as a special case of Henry's law. Students, now we are going to discuss Raoult's law as a special case of Henry's law. Students, according to Raoult's law, the vapor pressure of a volatile component in, say, liquid solution, in a liquid solution, now is what we say the PI, so it is partial pressure of one of the component, is equal to what? It's vapor pressure in pure state into mole fraction in the solution. So students, this is our what? Raoult's law. Or we can say the partial pressure of ith component of a liquid solution is directly proportional to its mole fraction in the solution. So this is our Raoult's law. Now students, in case of gas in liquid solution, so we are assuming that gas is solute. So now students, in gas in liquid solution, one of the component, that is gas, is so volatile that at room temperature it is a gas which is over the solution. So students, in such solution, the solubility of the gas in solution is a function of what? Mole fraction, or we say it is function of, the pressure of the gas. So according to Henry's law, here we apply what? Henry's law. Now the partial pressure of the gas, say it can be any gas, I लिख देता हूं, over the solution is directly proportional to the mole fraction of the gas in the solution, and mathematically we write it as what? Pi is equal to Kh into Xi, or so we can conclude from this that the partial pressure of the gas over the solution is directly proportional to mole fraction of the gas in the solution. So students, we have this conclusion. Now students, when we compare these two statements, we find that in case of volatile component, the partial pressure of that component is directly proportional to mole fraction of the component in solution, चाहे फिर वो Raoult's law हो या फिर Henry's law हो. So that means Raoult's law भी जो हमने अभी पढ़ा, so जो हमने पहले Henry's law पढ़ा उसी का एक special case है. So when we compare students these two statements, we find that this Henry's law जो है वो actually क्या है, Raoult's law is a what? Special case of Henry's law. ये जो Raoult's law है ये Henry's law का ही एक special case है. The only difference is that here one of the component is so volatile that it is a gas, whereas here the components are volatile but otherwise at say low temperature they are, or generally at room temperature they are liquid which tend to form vapors. So students, the conclusion is that Raoult's law is a special case of Henry's law. There is a small difference, however, and that is what? This part. The proportionality constant in Raoult's law is what? This is vapor pressure of the volatile component in pure state. Whereas here the proportionality constant is what? A mathematical constant whose value depends on temperature as well as nature of the gas as well as nature of the solvent. So these two laws are otherwise same. The only difference is in the proportionality constant. So student, this was Raoult's law as a special case of Henry's law. Now students, we are going to discuss ideal and non-ideal solution. That means the liquid solutions are of two types, ideal solution and non-ideal solution. Students, based on Raoult's law, liquid solutions are of two types. The first type of solutions are called ideal solutions. And the second type of solutions are called non-ideal solutions. So we have two types of solutions, ideal and non-ideal solutions. So students, first we will discuss ideal solutions. Now students, what do you mean by an ideal solution? Students, listen carefully. Solutions which obey Raoult's law over entire range of concentration and temperature are called ideal solution. So ऐसा कोई भी solution जिसमें उसके components Raoult's law को अगर obey करें over entire range of concentration, such solutions are called ideal solutions. So students, now we'll go into details of ideal solutions. So first important thing is that students, ideal solutions are formed by mixing two components which are what? Or which have identical chemical structure as well as nearly same properties. So these type of solutions are formed by mixing two components which have identical chemical structures and nearly identical properties. And students, the most important thing in case of ideal solution is that, say we have an ideal solution which is formed by mixing A and B. So these are the two components. Now students, in pure A, the intermolecular forces are between A and A molecules, and in pure B, the intermolecular forces are between B and B molecules. But students, when we mix these two to form a solution, the new interaction will be between molecules of A and B. Now students, pay attention. If these AB interactions, that means if the strength of intermolecular forces between molecules of A and B are of same magnitude than AA and BB, we say solution is ideal. So students, in ideal solution, these AB interactions in the solution, they are of same magnitude as AA and BB interactions in pure liquids. So this is students an ideal solution. Now let me tell you students, एक ideal solution दो different components को mix करने से बनता है. these components can be nearly same, but exactly same तो कोई दो liquids हो नहीं सकते, कुछ ना कुछ थोड़ा बहुत difference तो होगा ही. So students, listen carefully that ideal solution जो होता है वो rare होता है. Solution nearly ideal हो सकता है, perfectly ideal नहीं होता. So this is very important point to note that हम theoretically कह रहे हैं ideal solution, but practically speaking an ideal solution is rare. Ideal solutions nearly ideal हो सकते हैं, perfectly ideal कभी नहीं हो सकते, because AB interactions AA और BB के nearly same हो सकता है, exactly same तो हो ही नहीं सकता. But चलो हम बात करते हैं that nearly ideal solutions में these AB interactions they will be of same magnitude as AA and BB interaction. Now students, since ideal solutions obey Raoult's law, so therefore the partial pressure of A in that solution will be P naught A XA, because Raoult's law is obey, and therefore partial pressure of B will be what? It will be P naught B into XB. So students, total vapor pressure P in the solution, which is given by the sum of individual partial pressures PA plus PB, or it is equal to, according to Raoult's law, P naught A XA plus P naught B XB. So students, finally we say P, say this is observed and this is calculated, means theoretically. So P observed will be equal to P calculated. So students, this is very, very important that in case of ideal solution, the vapor pressure of solution calculated and observed दोनों same होंगे, which means there will be no deviation. So that means delta P would be 0, means observed or calculated vapor pressure of solutions में कोई difference नहीं होगा. So students, this was the basic elementary idea of an ideal solution. Now students, in next lecture we will discuss all the characteristics of ideal solution as well as we will discuss the non-ideal solutions. So students, that is all for today. Thank you.